Hello and welcome back to Lemaster Tech, and today's video is going to be a continuation in the Introduction to Controls and Automation tutorial series we've been doing in the channel recently. Today's video specifically, we're going to take an introduction to the world of wiring and electrical schematics for controls and automation. So this is a super important concept and aspect of controls and automation engineering. It's also kind of a tricky one to figure out a good intro video. So I want to start by briefly telling you how we're going to attack this sort of concept. So there's way more, just like all these concepts, there's way more than you could possibly cover in just one short introduction video for the world of electrical controls and automation. And so what we're going to do is we're going to take a look at some example control schematics, not of panels that I physically have here in front of me, but then we're going to take a look at some very basic schematics, create them from scratch together, and then we'll also take a look at the hands-on what that actually means in the physical world. So how every wire that you add to a control schematic actually communicates and translates into the real world. We're going to do a few hands-on examples together. So that's sort of the format here. If you have basic understanding of hobby electronics, like you've played around with Arduinos or Raspberry Pis, then this will be a cool way to see how it translates into the world of industrial automation and controls. And then if you've been an electrician or a maintenance technician or anything like that, this will be a really good way for you to see the controls and software piece of it, but you're probably pretty familiar with the hands-on piece already. So let's just dive right in. In terms of visual aids, it's going to be a little all over the place because I have some like very high level bullet points in a PowerPoint. Then we're going to take a look super briefly at the code we write, but then we're going to cut over to physical wiring as well. And again, the reason wiring is kind of a broad topic and a hard one to cover is because in the world of industrial automation and controls, a control panel schematic and a drawing package could be things that call out your devices and your actual sensor level connections to a control panel, and then all the PLC controller level connections. So from your PLC to I/O modules, input and output blocks, relays, terminal blocks and distribution, as well as connections to the devices and the sensors. And then your power distribution, usually a high power AC power feed into a control panel, and how it translates into DC or step down transformers to be used inside the control panel, as well as power feed to motors and VFDs and things like that. And then often your networking would be encompassed in that as well. So your Profinet or EtherCAT or Ethernet connections as well. So obviously it's a super broad concept, but the drawing package for a control panel is maybe the most important thing to correlate the physical world to the software side that are both so important for controls and automation. So super quickly, in an industrial control package, a really good drawing package, you'll usually have a view that looks like both of these. So this is kind of two different views. I'll try to drop myself in the middle here. This is kind of two different views most of the time. And what you've got is a physical rendering of the panel on the left here. So this has these green covers are usually plastic wireways called Panduit, or whatever sort of wireway that you have. It's just an industrial way of keeping your wires organized. As we'll see when we get to my hands-on examples, physical wiring in the field looks really messy if you're not zip tying or using cable glands and conduit and stuff to keep your cords really clean. So most of the time, these like gray or light green rectangles will be in a material like Panduit, and it'll be a wireway. But then this physically will look almost identical to the control cabinet when you swing the door open. So you have circuit breakers and power distribution and VFDs and PLC components in a very physical, realistic rendering. And then on the right, you have what's kind of called the wireframe, which is usually a slightly less but still precise, but slightly less precise physical rendering of the panel. But everything would be labeled with however it's getting called out in the drawing. So if you see, these are basically the same control cabinet, but on the right there are a lot of blue small text that's kind of hard to read, but there's a lot of blue labels calling these VFDs out as VFD 1070, 2070, 2190. Your switch in the middle row, terminal blocks, PLC components. And so this is a labeled one that still has all of the physical components in their correct physical locations. But this one is correlating a wiring label like VFD 1070 or whatever, some way that it's going to get referred to in this control package. And it's correlating that physical component to a drawing package page that we'll find. So if we look in this next page at an example page of an industrial wiring package, this is actually a great example of the whole drawing package once you get into the line level schematics, which we'll talk more about during this video. But to highlight a few things here, it's very common to have two columns side by side that have these wire numbers. That's kind of hard to see, but these line numbers from like 200 to 222, and often the wires will get physically labeled with whatever wire, with whatever row they're on in their drawing package. So it's very normal to see a wire label physically on a wire in a panel that says 205 or 225. It's also very normal to see their tag name. So if you have like a solenoid valve, it could say SV 500 whatever. But often the label will be a combination of where it physically is in the field and where it is in your drawing package. But anyways, you'll get these two columns side by side kind of drawings just because most wires don't merit a full page. Most schematics don't need a full landscape page. So they'll split into two columns. And then the footer is actually where I want to spend some time here because the footer of the drawing package contains an enormous amount of information. Usually on the left side, you have revision notes, which would be the person who approved a revision, the date it got changed, which revision number or letter it is, and then usually a brief note or comment about the revision itself, like what are you adding, what are you deleting, what are you changing. It's very normal to see the latest revision or the newest revision have all the changes in like a cloud or a bubble format on your drawing. And then there's usually some footer information about the company that the drawings are for, like, hey, this was for, you know, this chemical plant, prepared by this person, this address, whatever. So some physical information about the drawing package. And then over here is usually who prepared it. So you'll have like the engineer's name of who prepared it, who installed it, who, engineer or designer that was kind of behind that. More information about the customer. And then usually in the footer, you also have stuff on every single page that tells you the name of that page and then where within the broader drawing package you are. So on a huge control panel that has individual motor and sensor and device schematics called out, you could be on page like 12 of 158. So the numbering and the information in the footer is very important. To talk super briefly about some of the most common software out there, you have like like AutoCAD, Autodesk are some of the more common CAD software, and then ePlan is one of the more like software intensive CAD packages as well. But there's also some free ones online. You can use things like KeyCAD, which is best known as an electrical package for like designing PCBs, but you can do free schematics as well. There's a lot of online tools that are kind of free but have less powers. So I think Autodesk, AutoCAD, and basically ePlan are like probably the two biggest competitors in this space. But there's plenty of companies that do this just like any other piece of the industrial automation and controls world. Okay, where do you begin? If this is a beginner intro to control panels and schematics, knowing that the footer has great information, knowing that there's usually a title page, knowing what software to download, that's all great. But briefly, some talking points. So to remind you, this is an introduction and not a comprehensive lesson. And then if you Google just control package, like electrical panel wiring examples, there are some really good ones out there that actually show you physical ones in the field, and they talk you through what you're physically looking at and everything else like that. So if this in particular is the aspect of controls and automation that you really want to become super proficient at, I suggest you just do some Googling. This Solus PLC, another great online company, Real Pars, has some other good examples, and they actually talk about individual components and schematics that you'll see in the field. So that's not a cop-out. This is meant to get you familiar with the basics, but it's also just not a deep dive. So if you want to spend a lot more time studying on this, I absolutely recommend just spend some time Googling. Solus PLC and Real Pars have some great examples, as well as some others out there. Okay? But then I do think one thing that's really important to talk about as part of this video is who has standards in this field. So if you're a drawing designer or an electrician or an instrumentation and controls engineer, it's very important to be familiar with NFPA 70, NFPA 79, and UL 508A. Also sometimes called NEC 70, but basically these are industrial guides on power requirements, power distribution requirements, best practices for installing and creating and developing control cabinets. UL, or Underwriters Laboratory, is a listing that like panel fabrication shops and places that develop controls equipment, they want to stamp their panel with a UL listing because that means they've adhered to a certain high standard that gets validated by this company, by the UL organization. Those are like 1,000-page guidelines and books, and usually I think you have to pay for a whole copy of them. Best practices of those are found online. They talk about wire gauges, power distribution concerns, and a lot of other really great things to keep in mind while you're developing control panels, but not really what we're going for in today's video. So those 3 standards are great for looking into. But let's talk more practically. If you're a hobbyist or a field engineer who just needs to know when I need information, where can I go to get said information? And it's really the internet. But anytime you buy a sensor or a switch or a button or a motor, the manufacturer of that component should be providing the wiring schematic and information to you via internet manuals, downloadable manuals. Ideally, it would be included with the component when you buy it. But just a quick Google, or if you're buying components from Amazon like I do for my garage all the time, the Amazon listing itself oftentimes has the wiring called out as well. And then control components, these are actually a lot more standard. So if you're buying Allen Bradley or Siemens or Beckhoff or even, Arduino PLC like we're using in this tutorial series, they have really good pinouts and wiring schematics. They can take a variety of forms, so they won't always look like something you can easily drop into a wiring diagram, and they won't always have a 3D model that you can include in your panel. Sometimes you just need to make a little rectangle and say, hey, this is, this device or anything like that. But the actual wiring of how to wire a component comes from the manufacturer you buy the component from. So you don't have to do any guessing of how these things work. And then why it's so important and why it's worth a whole video during this tutorial series just to talk about this component is because in the world of industrial automation and controls, and honestly in the tutorials that we're doing just in this series, control panels and control systems get very large very quickly. And so manually tracking down every wire and cable, where it came from in the field and where it landed in the panel, it's not always safe. It's not always feasible if you've tucked things into conduit runs or they're in, an explosion-proof building, but your control cabinet's on the outside, or even wireways inside of Panduit tends to get so full that you can't just trace your wire accurately. And it's also just faster. If you're the person trying to hook up a system and you're in the field and it's 2 in the morning and you've been on site for 48 hours straight, you want an accurate, well-documented control panel schematic rather than guessing, trying to find a spare channel on your PLC, trying to look into the code and see if there's a spare channel by like reverse engineering the code. So understanding the electrical schematic importance of industrial automation and controls is super pivotal. Okay, so that was a lot of Pete talking, which is my least favorite kind of video. I really like to show you guys things and do engineering together. So let's get into a practical example, and let's just start because I really want this to be a tutorial series that's low to no barrier to entry, right? I'm gonna make all of the electrical schematics today in this example for you in PowerPoint. I don't want this to be like, oh, as long as you have ePlan or as long as you have AutoCAD, you can follow along. So for an example, let's take a look at a system that has a power supply, a PLC, and one input, which is just going to be a hand switch, okay? So a, on, off hand switch, and then a PLC and a power supply. And I think I also, when I prepared these schematics, I had 12-volt power supply called out. I think I've got a 24-volt power supply on my DIN rail right now. That part doesn't matter too much because the pinout's the same, and the Arduino PLC can take between 12 and 24-volt power supply. but nobody yell at me in the comments. If this schematic says 12 volt DC and the actual power supply says 24 volts, I will ignore your yelling. I want to talk about what I have on the screen right now because, like I said, I'm making this in PowerPoint. These are not, shapes that you download from the manufacturer, anything else like this. This is literally just, I have a power supply that takes wall outlet voltage. And then this power supply gives me 2 plus and 2 minus. So 2 0 VDC and 2 12 volt DC channels. I need the Arduino PLC to receive power. So it has 2 positive terminals and 2 negative terminals as well. And then it has 8 input channels, and then it has 4 relay output channels. So if you've been following along with the tutorial series, you've seen the body of the Arduino already. I'll have some pictures of it on screen now as well. But this is a simple rectangular representation of the component that we're dealing with. And then my hand switch has 2 different sets of terminals on the back, labeled 11, 12, 23, and 24. And it's just 2 different strips that are made when it's in the 2 different positions. So that's my hand switch. Let's take a look at what a not industrial control cabinet schematic for this system might be. Okay, so this, again, just in PowerPoint, no fancy software or anything. I'm using a solid blue line to show my DC positive power. And then I'm using kind of a white and blue. White with blue stripe is very common in the world of electrical controls for 0 volts DC. Or just solid white is also very common. But basically I have black, white, and green from the wall outlet into my power supply. And then I'm providing power and 0 volts. So these 2 wires make up a power loop to the Arduino PLC. And then I'm using another positive lead off the power supply to go into the hand switch. And then when I turn the hand switch into position 1, which is basically connecting terminal 11 and 12, then power will flow through this hand switch and go to input 8 on my Arduino PLC. Okay, so it's a very simple electrical schematic, and I'm going to tie it to this structured text program right here, which is just going to turn the blue light on when the switch is on, but then I'm going to use switching logic. So rather than just a boring like, hey, turn the green light on the body of this PLC on when the switch is on, I'm going to actually do a little bit of switching logic. So every time I turn the switch to the on position, that's going to switch my internal on-off variable, and then I'll switch an output and a little green light based on that. That was probably a poor, brief example, but the structured text tutorial was 2 videos ago. This is about wiring. So let's go ahead and take a look physically at the wiring for this system. And you can see the exact wires that are called out in our schematic show up on here. We have the black, white, and green wires coming out of the outlet. And then we have 2 blue wires going into the power feed of the Arduino PLC and onto terminal 11 of the hand switch. And then on the outlet terminal 12 of the hand switch, it goes into input 8 on the Arduino PLC. And then the last wire we need is a V minus or 0 volt DC return wire to the power supply from the Arduino PLC. Every wire that we have on this schematic shows up physically in the world exactly as it's drawn here. And let's take a look at a more industrial example of this. So this kind of looks more like you should expect to see in an industrial control cabinet. Okay, I'll try to drop myself in the middle where I don't block anything. But this is sort of how you would expect to see that show up in an industrial control cabinet. You have on the left, you have your AC voltage in, you have line 1, neutral, and ground, and then they go into a power supply. And you can see here, like I put the actual part number of the power supply that I got from Amazon. That's very common too. So you'd see maybe PSU1, like power supply unit 1, and then a part number for it. And then the pinout has ground, neutral, L1, and then plus, plus, minus, minus. Typically, these are grayscale control panel drawings as well. They don't have to be, but you saw in this example a lot of color, where I was kind of color coordinating, matching what's in the field with what's on the schematic. I do actually really like doing these sorts of schematics for hobby circuits because I just think it's clear. But when you're in an industrial setting, this is what you'll be dealing with more frequently. So you have the same Arduino PLC here. Again, I dropped the power supply or the part number on it. And then you have the DC outlet power feed of 0 volts and 12 volts, kind of becomes your new power rail on the left edge of the right half of my screen. And here you can see the power coming into the PLC and then going through a hand switch, which is represented again by the part number, and into input 8. Okay, so actually what's important to know is that what you're looking at here is very industrial, and what you're looking at here is sort of hobby. But you'll see schematics that look a lot like both of these depending on your setting and the size of your application. So that's our first practical example. We have one more slightly more complicated practical example, and then we're going to wrap this video up. Okay, so we have our industrial / hobby example. Let's add an output. So we have a digital input in this previous example, and that's our hand switch. Let's go ahead and say we want to add an output, and it'll be an outlet. So we could hook any common household appliance we want up to a standard outlet. And to do that, we need L1, neutral, and ground. So we need that same 3 wires that kind of come into our power supply. We need those hooked up to an outlet, but L1 needs to pass through a relay. And a relay is a super important controls component, which allows us to switch a wire between multiple contacts. So you use low voltage DC power to change the state of a relay, and then a separate electrical connection is made on the other side of the relay. So I think we'll probably get more into relays as we continue doing the tutorials in this series, but it's arguably the most important component in the world of industrial automation and controls. So let's take a look at the hobby version of this circuit now, okay? And let's walk through all the wires that have been added. I also put in one new sort of color convention, which is a wire that ties directly into the PLC. I've changed to orange, where in the previous example I just left it as blue. So basically the final PLC signal wire is orange. L1 on this schematic is represented in black, so that's going to be your 120 volt hot. Neutral is going to be kind of this light gray because white didn't really look good on a white background. Ground is green, and then everywhere that's 0 volts DC is represented by this like light blue, white and blue striped wire. And then dark blue represents your 12 volts, which in my physical setup is actually 24 volts. But what you can see here, what's actually changed, nothing to do with the hand switch or powering up the Arduino PLC. But what we've done is we've added a hot wire, so a 12 or 24 volt DC wire from the second terminal of the Arduino PLC out feed to side 1 of the relay output on the Arduino PLC. And if it seems silly to go from a relay to control something, it is a little bit silly, but actually I wanted to show you guys a DIN rail mounted relay rather than just a relay PLC output. Technically, there's an extra component in here because I have a relay output and then I go to a relay. Let's just take a look at this practical example, okay? So when the PLC energizes that wire, this relay connects the common to the normally open channel. And then when the coil releases, the common is connected to the normally closed channel. That's a super important concept, not just for relays, but for sort of all of electronics. So if you look up relays and common, normally open, and normally closed, you'll learn a lot about sort of switching voltages. But for now, just know that to control the state of the outlet from our PLC, we bring 120 volts hot into the common channel of our relay. And then normally open means it is the one that's not going to be connected until we pull that coil in. So you could technically program the circuit to work in normally open or normally closed. We're going to use normally open, meaning the only time that outlet will be energized is when the relay is energized, which is when the PLC tells that output it's true. Okay, so that's the schematic. Let's take a look real quick at what this physically means on our bench setup. And you can see, just like I said, it's the exact same wiring as before, but now we've introduced this new relay, and we have the additional power feed from the Arduino coming into channel 0 of the output, and then we have the channel 1 of the output going to the A1 and A2 coil side of the relay. And then the other side of the relay goes back to 0 volts DC. And then we have the downstream power feed of our relay switching the common wire between normally open and normally closed, and the normally open signal goes to the outlet. So we actually didn't have to modify our PLC program at all for this one. All we did is we just said, in addition to having L1, which is the light on the body of the PLC, we now also want the outlet to turn on and off, and we just tie our outlet. If we look at relay outputs, we just tie our outlet to the first output channel in the PLC. So if you've been following along with the tutorial series, that whole PLC side of it should look pretty trivial. Don't worry too much, because this purpose is to be hands-on and physical and electrical, rather than software heavy. But feel free to ask any questions you have about it in the comments below. Now, same as before, let's take a look at how this would get represented in like a physical, in a more industrial controls package drawing. So let's take a look at what's changed. We still have the power feed on the left going through our 24-volt power supply, which I know I called out as 12 volts in here, but it's 24 volts on my bench setup. Sue me. Anyways, and then I did something interesting that I think is useful to call out on this channel, or on this tutorial, is I labeled two wires with numbers, O1 and O2. And this is a massive simplification from how like a large control panel would do it, but it's not always feasible to show every physical connection in your drawing in a continuous one nice clean view sort of way. And if you look at the relay, which we've added to the top right, you can see output channel 1, wire 0 and wire 1 are pulling in the A1, A2 coil side of the relay, just like we saw before. But O1 and O2, which are linked to these, are actually being physically represented by a number that says, hey, there's this disconnect between over here and over here. And sometimes you would want to link it with some additional letters as well, or anything like that. But this is just a way of calling out that the other side of this wire shows up somewhere else in your drawing package, and it's a way for you to correlate and track down those wires. Again, this is sort of a non-sustainable way. As you get into bigger and bigger and bigger systems, you can't just keep drawing this like function block diagram of all of the crazy wiring schematics, and the coloring conventions can get out of hand and they're sort of arbitrary. So you start to see, as systems get bigger and bigger and bigger, how essential having like a standard format drawing is. So this industrial example, which honestly I've already sort of deviated because I'm building it in PowerPoint, from like some common design choices. But I hope the basics are clicking for you here of what you're looking at, how the physical world maps onto this sort of electrical schematic software world, and then what you're actually looking at in the field, and how that ought to be documented when you go and grab a control cabinet. Okay, so I know by far in this tutorial series, this is the most talking that I've done and the least showing you things that I've done, but it is really hard to demonstrate the world of electrical controls, drawings and schematics and control panels without like going into the field and walking through one with you. And frankly, my company would not be okay with me like walking around the plant floor showing you our control cabinets. So you're gonna have to do with what I can show you in the garage. I hope it was useful. As always, let me know with any comments or questions on this one. I also have a pretty deep library of me talking about controls and automation concepts, including wiring and hardware and things like that on the channel. So be sure to check out Lemaster Tech for more. Drop me a comment with any questions that you had, anything that I can try to clarify for you, and let me know what you want to see more of on the channel next time. Thank you so much for watching, and we'll see you next time. Thanks. Bye.